Okay, so hello and a warm welcome to all. Welcome to one and only present here. Today we have gathered here for an exclusive webinar, which is titled as Speech Signal and Processing Technology and its Applications. And today, for delivering this, we do have with us our today's expert, uh, Dr. Rajesh Kumar Dubey. He is a PhD in and MTech. He is an HOD of Department of Electrical Engineering, Department School of Engineering and Technology, Old Academic Block, Central University of Haryana, Mahendergarh. He is specialized in digital signal and speech processing, machine learning and deep learning, and control engineering. So without wasting much time, let me welcome Dr. Rajesh Kumar Dubey, sir. Welcome, sir.
Thank you. Thank you very much. I am Dr. Rajesh Kumar Dubey, and the topic of today's webinar is speech signal and processing, technology and applications. And this will see what speech is, what speech communication is, how it is defined as a speech signal, what speech signal is. What is the requirement of its processing from engineer point of view? As engineer, how we can model this speech signal, and what processing tools, signal processing tools can be applied on that to process the signal, and what are the different applications, it's technology, and from applications point of view, if signal is there, if we are processing it, then where and how it is going to be applied, that is the application point of view. We'll see here and try to understand what the speech signal is and what are the processing techniques, what tools we are using, and okay, and then what are the technology and applications that we have to speak. Okay, that will start. See, this is general structure of speech communication. The speaker is speaking something. This is in form of air, turbulence, air pressure, variation in air pressure, and that is going through a medium, and it is going to reach to ear to an listener. Listener will listen and understand it. In this case, at both the end, biology is involved. At sending end, that is speaker, and its a speech production model, and at the receiver end, human ear and its auditory system. In normal, when we are sending data, from sending end, data is there, receiving end, data is there. And in channel, it is signal in form of data. Here at sending end, first of all, you have to understand the biology of speech production. Similarly, at receiving end, we have to understand the biology of hearing system, human hearing system. So this is a general speech communication model. Speech is a articulation that produces sound waves. It transmitted through a medium to human ear. That is written here. That means how a thought is coming. That idea is, it is shown here in form of model. How an idea is coming, and how that idea coming air from the lungs. So this is steady air. How this glottis is varying, it's making its producing some frequency, and then this articulation and speech sound coming out from the mouth. Similarly, after that is reached to the human ear, the ear conveys the received sound. Here, sound is received to the human ear, and it is again going through the ear canal, going down eardrum. So all this processing That is the biological process, biological processing. And then the spikes going to the our brain to understand it. Then perception is made. So at the starting, at sending end, it is speech production, speech articulation. And at the receiving end, it is ear. Meanwhile, this transmission is simple. It is transmission of data. Speech signal properly transformed and made in form of data, and now it is transmitted like any other communication system. So in our speech communication system, this will be channel, this will be the sending signal, this will be the received signal. So this is a general model for speech communication. Here we have to understand how this speech is produced and how we can make or how we can make a speech production model from engineering point of view. And then how before transmission, how the signal is processed. This is speech production is, in our case, that will nothing like a system. Okay. Again, this signal and that's process signal. Then again it is received. Then again it is processing. And then finally, there is one system is more, involved at the sending end. One system is involved at receiving end. Meanwhile, transmission system. So this is general overall structure of speech communication. We have to understand from engineering point of view how this speech production is modeled, how this human hearing system is modeled. Once the speech production side and hearing side, they are modeled, it becomes a simple, like any other discrete time digital system, where a signal will be there that will be produced by a system. It will be transmitted, again processed, it will be received, receiving, and it is processed. So how we are going to model this speech communication, this biological system, to a digital model, so that digital signal processing tools will be applicable. So as an engineer, we can think like that, that signal produced, transmitted signal, and received signal. That's all. Once this speech production biology part is modeled, once human hearing system is modeled, this complete speech communication system becomes simple digital signal processing application. So that will be there. That we'll try to understand. Moving to the next slide. So this speech communication is like a speaker. It is speech production part, sound pressure wave, transmission part, listener, speech perception part. This is called a speech chain. Production and idea of thought will come into the mind of a speaker. Then there will be some neurological, biological processes. Then some muscular movements of our mouth. Then some acoustic sound pressure will coming out of the mouth of the speaker. And that is the speech. We have to model it as a signal. In our case, from engineering point of view, it is signal. Again, as a signal, this will be transmitted. Transmitted part is like any other communication, a signal is transmitted. Then listener will listen it. That is perception part. Acoustic sound pressure wave going to the human auditory system. Then neurological signals will be processed, and the idea of thought will perceived by our listener human mind. Okay. That will be there. This is called a speech chain. A speech chain. I think we understood speech communication. Speech production model. Here will that will be the signal, and that will call it a speech signal. Speech signal will mainly have two parts here, voiced and unvoiced. Whatever language is there, but all will have some voiced part or some unvoiced part. Hearing and perception, that is the human auditory model. And because signal is involved, so as digital signal processing tools will be applied, and as an engineering point of view, we can understand it as a time and frequency model. And we'll do analysis that is in time domain and in frequency domain. Speech signal, like any other signal, as engineering point of view, what we are doing, we are taking its time domain and frequency domain from analysis point of view. Similarly, speech signal will be also analyzed in time domain and in frequency domain. This is speech signal and its processing. From processing point of view, we can use once a speech signal, speech production and perception is modeled in form of digital signal and digital system type of thing, we can apply digital signal processing tools like Fourier transform, Z transform, okay, DFT, FFT. So all those tools will be applied. Once it is modeled as a signal, production of signal, transmission of signal, and receiving of signal. Once it is modeled like that from engineering point of view, so then now it can be processed as signal. And that's why all digital signal processing tools will be utilized as per the requirement, like Fourier transform, Z transform, DFT, FFT, wavelet transform, all these things as per the requirement and application. So that digital signal processing will be applied. The tools will be applied. A typical waveform of a speech signal is something like that. Once you will model and you plot this digital signal, speech signal, this is speech signal, typical waveform of a speech signal is like that. Or horizontal axis, time axis, or corresponding discrete time instants, and vertical is amplitude or magnitude. Major applications area of speech signal and its processing, that is speech compression, coding, like any other signal. First we are coding and then transmitting. Signal is not transmitted in digital communication. All we know that a signal is not transmitted as it is, but it is transmitted through proper modulation system. And that's why coding of signal is required. Here coding, that is called speech compression coding. Okay, so different type of codings are there. So this itself is a major area of speech signal processing. Other, you all must have heard speech recognition, speaker recognition, speaker verification, identification. So all these are areas of application of speech processing. Text to speech synthesis. You are having some text in form of written material and you want to convert it as a speech signal so that it will feel like someone is speaking. A machine which can translate text to speech signal is a speech synthesis problem. Quality estimation of a speech signal. Once a speech signal is transmitted, at receiving end, some degradation is possible. And that's why quality estimation required, whether it is below the threshold or some improvement or enhancement is required, so that listener will be or customer will be satisfied with the received signal. That's why estimation of quality and its enhancement of degraded speech signal if quality is below the threshold. So that is there. So these are the major applications areas of speech signal. Nowadays, we are using mobile phones, computer, laptop, and in one or other way, everywhere speech processing is going to be happen. Whether it is video signal, whether it is speech signal, whether it is audio signal, whether it is music, or in television, sound is coming in form of signal, that is audio signal. So this processing of audio signal in this electronic gadgets almost everywhere is needed and required and going to happen. That's why understanding this speech signal and its processing and its applications are very much emerged areas, and also after developing of many latest techniques, deep learning, machine learning, artificial intelligence, or it is going to be very helpful and important areas of speech signal and its processing. That is it. The typical waveform of speech signal is expanded for a particular utterance and phoneme level. It is shown in this diagram. This diagram, it is speech signal waveform with phonetic level for the text message, like should we chase, taken from Raviner and Safer book. Okay, so it's a very good book taken from Foundation and Trends in Signal Processing, and that book is from L.R. Raviner and R.W. Safer. Here, phoneme level plot is shown. What that phoneme is, the smallest unit of the sound wave, speech wave is we are calling phoneme. The smallest unit of this speech sound, like should we change, should. First coming out to be sh sound, should. Then u sound, u. We can see here, sh sound is looks like a noise, and u sound is some magnitude is there, and some periodicity type of thing. Like here, little, not exactly, but some periodicity. This pattern is repeated, and less similar pattern is repeated, and so on. So something you can say. Here it is a voice sound, sh, u. U sound is some voice sound. So some periodicity and more magnitude we are observing. Should, the sound is unvoiced sound, and that's why very low magnitude we observe here. Similarly, wo, we, and the e sound, that is a voice sound, and that is looks like some periodic. This type of periodicity is called quasi-periodic. Actually, signal is not completely periodic, but signal is periodic in small section. Like see, this part from signal more or less periodic for this range. Similarly, sa is looks like some noisy type of things. Okay, a sound is looks like a high magnitude and some periodicity. Again, choose sa. So we say za sound, some unvoiced. So here from this pattern, once we are drawing this speech signal at phoneme level, we can see that in this example, should we say that voice sound and unvoiced sound. Unvoiced sound looks like some noise and smaller magnitude, and voice sound, vowel sound, we can say vowel sound or voice sound, they are high magnitude and quasi-periodic. Not completely periodic, here we call it quasi-periodic. Okay, section-wise periodic. It is called section-wise periodic. Okay, so where voice sound is there, some periodicity there, more magnitude, and otherwise unvoiced sound, low magnitude, and some noisy type of differentiation. So on that first observation, we can analyze this as a signal and smallest unit, that is phoneme, and this is phoneme level presentation of a speech signal. So hope you can understand this, that what this speech is, what that phoneme is, how it is broken in form of phoneme level, and which phoneme sounds like voiced and which phoneme sounds like unvoiced. Unvoiced part is noisy type of things. Voiced part is some quasi-periodic, high magnitude. High magnitude means high energy area. Some periodicity is there, energy is more. So this is the first observation on analysis of speech signal on phoneme-based level. So I think this idea, you must understand this idea. And this speech production. Now we'll analyze in little bit deeper and little bit more. Sound is flow of air from lungs, vibrating vocal cords. So actually, thought is coming in mind, and accordingly, air is pushed from this lungs. It is coming at where the vocal cord is there, which vibrate, opening and closing. That is also called glottis, and this vocal tract. That this human mouth system, and that sound is coming out from that, and that is the speech in form of air pressure. The speech production cavities is called vocal tract, like our tongue, upper palate, lower palate, teeth, this lips, all this include in this vocal tract part, that is speech production cavities, lips that will radiate the sound, and after lip sound will coming out. Sound may be coming in form of vowels, voice sound like a, e, o, u. All these vowel sounds are like voice sound. They are having high energy area, quasi-static model, quasi-periodic model, and fricative sounds. Some other sounds are unvoiced. Unvoiced may be fricatives and plosives. So whatever speech sound is coming out from the mouth, that may be voiced, they may be unvoiced. Unvoiced part is merely two parts, that is fricative sound and plosive sound. Fricative sounds are those which need some friction type of thing, some friction, like f, s, z sound. These sounds need some friction, okay? And some plosive sound. Plosive is when closer is there, sound suddenly sound close, like pa, ta, ka. These sounds are sudden closure, produced after certain closure. These are called plosive sounds. Unvoiced sounds are in majorly two parts, fricative sound. So we have to analyze and we have to understand. Then only we will be able to do the analysis from or using the signal processing tools. So that means voiced part, vowel part sounds, unvoiced sounds, unvoiced maybe fricative sounds, maybe plosive sounds. So this is our speech signal. Slowly we are trying to understand this speech signal slowly deeper and deeper. That we should understand what this speech signal is in the speech production. And then this speech production should be modeled as an LTI system from DSP point of view, digital signal processing point of view. This thing we have to model. If we understand this, we can model as a system, and that will be LTI system. That means now speech production is a model which produces sound. Sound may be voice sound, maybe unvoiced sound, fricative sounds, plosive sounds, like that. So here, on the basis of that, we will say the types of excitation. We'll say the name excitation. That is, what type of sounds is coming, it depends on actually excitation. What the input is pushing air from the lungs. Actually, sound is coming out of mouth in form of voice sound, in form of unvoiced sound. So this unvoiced sound is produced by forcing air through the glottis or an opening between the vocal cords. This is the vocal cord vibration. Voice sound is coming when vocal cord vibrates. That is opening, closing, opening, closing. That glottis vocal cord is opening, closing, opening, closing. That means some periodicity is involved, some frequency is involved. This we'll call as a fundamental frequency of that particular speaker. Later on we'll discuss as a fundamental frequency. Okay. So this opening, closing, that means some periodicity will be involved, some frequency will be involved. And that's why that particular part, voice part in the signal, is coming in form of voice, that is quasi-periodic form. And unvoiced sound is like low magnitude and noisy types of things. Okay? It is generated by forming a constriction at some point along the vocal tract and forcing air through the constriction or to produce turbulence. It is producing some turbulence type of things. And that's why some noisy sound is coming, like sa, za, cha, all this. So in this case, there is no vocal cord vibration. And that's why no periodicity will be involved. So that is there. Vocal cord vibration, it is voice sound is produced. When there is no vocal cord vibration, unvoiced sound will come. So that is there. A typical pattern we can plot like this. So you can see voice sound looks like some periodic type. That's section-wise plotting. So whatever section in our speech signal that will be voice, that will have some periodicity. We call it a quasi-periodic. A similar pattern is repeated. Okay. We'll see it's in frequency domain. After taking the Fourier transform, it will be something like that. That envelope is there, and some this pattern is there. It is in a lower frequency range. You can see this is 1000, 2000, 3000. So this is in lower frequency range up to 8000. Okay, that is there. And magnitude is, when say magnitude is more. But when we look on the pattern of unvoiced, in time domain, it looks like some noise type of things. And in frequency domain, you can see in the lower frequency, less content is there. In higher frequency side, more content is there. That means high frequency noise. You can say unvoiced sounds are high frequency noise, and voiced sounds are quasi-periodic high magnitude signal. The complete speech signal is divided into two parts. Voiced part, which has quasi-periodic, high magnitude, high energy part. Unvoiced part, low magnitude, high frequency signal, or you can say noise. That is there. From digital signal processing point of view, now our speech signal divided into two parts, voiced and unvoiced. Unvoiced part is noise. Now we'll say unvoiced part is noise. Okay, and if we can see this pattern, so this is some envelope. For this voiced part, we'll see some maximum point like F1, F2, that is maxima of the envelope. These F1, F2, F3 are called formant frequencies. As I told, the vibration of vocal cord, that is called fundamental frequency of the speech sound, voice speech sound, or periodic speech part, that is fundamental frequency, or fundamental, or that we are calling as a pitch frequency or pitch period. The corresponding period is pitch. So that pitch frequency and pitch period is coming from that. So that is due to vibration of vocal cord. And other frequencies are called formant frequency. Once vibration is coming from vocal cord to our mouth is doing some resonating type of things. Like complete mouth, that we call it a vocal tract, and that is producing a speech sound out of the lips. So this vocal tract is resonating at certain frequency. These are called formant frequencies. The formant frequencies are resonance frequency of vocal tract. And fundamental pitch frequency is frequency of vibration of vocal cord. So if you will see this spectrum, we will plot in frequency domain, you'll sharply see that some this formant frequency F1, F2, F3. So normally this F1 is around 300 Hertz, F2 is around some 3000. This will vary speaker to speaker. So these are the formant frequencies. Formant frequencies are frequencies of resonance of vocal tract, mouth. That is all the tips, teeth, lips, tongue, upper palate, soft palate, hard palate. All this constitute this vocal tract. And vocal cord, that is vibration of vocal cord, that is pitch frequency. So two types of frequency are there in the speech signal: fundamental or pitch frequency and formants or formant frequency. On the spectrum, you can visualize it. So this speech production, it is in two parts: voice part and voice part. This is the speech production of voicing part. How voicing part? Air comes from lungs, forces it way through vocal cord, pushing it open. This causes air pressure in glottis to fall. Because of drop in pressure, vocal cords step together again. That is the speech period. This is acting as the impulse train generator, and that is vocal cord vibration. That is glottal pulse model. So some like this PN is coming, or some gain is adjusted, and that signal after gain we are getting that as UGN. UGN is output of this part. We can model like this. This impulse train generator. Pitch period is introduced by a vibration of vocal cord. So we can draw the spectrum like this. And this gain adjustment minus 10 dB per dB. So this is now this analysis is from speech signal point of view. That is seen in frequency model. So in frequency model, this formant because F0, 2F0, 3F0 will be shown. So these are the formant frequency. You see here, these are the formant frequency. This F0, 2F0, 3F0. Okay. And this F0 is one, that is the fundamental frequency. So this is the 2F0, 3F0, 4F0. These are the different frequencies. So this F0 is 1 upon pitch period. What F0 is? Fundamental or pitch frequency. And pitch period will be related inversely like that. So like any other pitch, any frequency and period. And that's why pitch period and pitch frequency are. Okay. That is there. If we can see in terms of how much air volume is coming per second, so we can see like that some pattern is followed. So some equal amount of air per second, almost equal. So that it look like periodic. So this fundamental frequency, we are calling it a pitch frequency, and corresponding pitch period, that is normally male it is 132, or it can range even from 50 to 250. And for female, this fundamental frequency is more, like 223, in the range of some 120 to 5. Female pitch frequencies are more, and male pitch frequencies are less. So that is a general observation. Other important part is unvoiced production. Speech, I said, a speech is now two parts. Voiced production, the voicing part is because of vocal cord vibration that introducing frequency, fundamental frequency, formant frequency. From a DSP engineer point of view, we think like that. That is when we are speaking, speech production model, lungs, vocal cord, they are introducing frequencies in the whatever air is pushed from the lungs. And that are fundamental frequencies, and again vocal tract that is introducing frequency, and they are the formant frequencies. And when we are talking about voiceless or unvoiced sound, unvoiced already we have observed in time domain representation that it looks like noise, random noise generator. So when we are talking for a speech communication and its transmission point of view, no need to transmit unvoiced part because it's a random noise like the things, and we can generate it locally at the receiver end. So to reduce the bit rate of the speech signal transmission, we can focus only on voiced part of speech signal. Unvoiced part can be locally generated as a random noise using random noise generator. In this case, air just comes from the lungs. Vocal cords are open, air passes through the unobstructed, so no opening, closing, no frequencies introduced from any that vocal cord side or glottis side. If the air moves very quickly, the turbulence causes a different kind of phonation and whisper sound. And this is almost like random noise, white noise type of things representation can be used for the representation of unvoiced part. So when we are talking for transmission of speech signal, we will separate out voiced part. We will focus on voiced part because information is there only in the voiced part. Information in terms of frequency is there in form of fundamental frequency, formant frequency, that is there in voiced part. So we'll focus our attention on voiced part. Unvoiced part is like a random noise generator. So this is speech production model that UG is coming from that. This vocal tract model, which is going to introduce formant frequency, and then lip, which is going to produce it like a rip radiation model, then final speech output. So the vocal tract forms a resonator for the volume resonance signal, but just as told that it will introduce frequency, those are called formant frequency. Formant frequencies are a resonance frequency of the vocal tract, like F1, F2, F3, which will be like 2F0, 3F0 in terms of fundamental frequency. Fundamental frequency is introduced by vocal tract vibration, and formant frequency, that is vocal tract model that will introduce these frequencies. Lip radiation model, lip will just produce sound such that it will fit with the normally minus second order, minus 6 dB per octave, which represents it is like a second order filter. So some F1, F2, F3 frequencies, which are formant frequencies. This F0, and these are the integral multiple of that other, like 2F0, 3F0. F0 is fundamental frequency, pitch frequency. F1, F2, F3 are, these are formant frequencies. Complete speech production can be modeled like it is a combination of voiced part, combination of unvoiced part. Like a switch is there, which is selecting when voiced part is produced, impulse train generator, glossal pulse model, voiced gain, and speech sound. Again, when unvoiced sound is there, like white noise generator, unvoiced gain adjustment. Okay. Hello.
I guess there's the disconnectivity of your screen share.
So I did not go to display. I'm retrying. Is it okay now?
Yes, sir.
Okay. So this universal speech production model is actually modeling two parts. Upper part is for voiced sound or lower part is for unvoiced. And here like a switch is there. When we are speaking out, when we are producing some speech signal, that means automatically our mind is adjusting on that switch, that when we are producing a voice sound and when unvoiced sound. That vocal tract filter is introducing formant frequency. Then radiation model, that is our lips. Lips is we are calling as a radiation model. Here we can produce this as a filter, which is having formant frequencies, this lip radiation model, which is converting into a second order system, and then output speech. This is our complete speech. So these first part up to here, where just vocal code vibration information is there. We call it is speaker dependent parameters, because vocal code vibration, that is fundamental frequency, varies speaker to speaker, and speech dependent parameters like formant frequency, lip radiation. This is speech dependent. All speech needs and what speech, what thing you are speaking, it is depending on. So this is complete model is divided into two parts: speaker dependent and speech dependent. Upper part is for voiced and lower part is for unvoiced sound. So this is the, now we understood the speech signal as a voiced, as a unvoiced speech production model. And when the processing parts come, now it is like a digital signal and we can apply speech processing technique. But when we'll go to apply for speech processing tools, we'll talk for short time. As I said, complete speech signal in two parts, voiced and unvoiced. Entire signal cannot be utilized for processing. The reason unvoiced part is normally not relevant for us. Only voiced part, where periodicity and high energy is involved, that is of point of interest. And that's why we'll focus on that. And that's why we'll calculate short time, not energy for the entire signal, energy only for voicing section. Or first we'll decide which section is voiced, and then calculating that is short time energy. That's why the name short time. Short time average magnitude, short time zero crossing rate, short time autocorrelation. All these terms like energy, magnitude, zero crossing, autocorrelation, we know in digital signal processing. But here we'll calculate for short time. And on that basis, even we can decide part is voiced or not. If it is voiced, we'll focus on it. Unvoiced, we'll not focus on it. Unvoiced, like random noise generator, that signal can be generated locally. First, we'll decide voiced part, and then we'll focus our all attention to only voice signal. So that is. So for that thing calculation, we'll take short frame, that is called a short time, like interval 1, interval. We'll select the such that, for example, I'm taking the section of 20 milliseconds. So first 20 millisecond, 20 millisecond, but we'll select first interval and one overlapping interval, like 1 to 20, then 11 to 30, like that, so that no information will be lost. Overlapping frame should be there. We'll call here name as a frame or frame block. Frame blocking of, for example, 20 milliseconds. This will as a first frame, this will be second frame, so that there will be overlapping of frame, so that no information is lost. And for all frame, we'll calculate short time energy, short time zero crossing, like that. So this will be the way of processing called as a frame by frame processing. So this is the calculation of short time energy, formula for short time. What we'll do in normal calculation of energy, we'll take signal X and find its energy from M minus infinity. But when we are doing for short time energy, we'll multiply the complete signal with a short time window or window of that size, rectangular window. W is rectangular window. And we'll multiply and then we'll calculate. Then this will give only energy for that length of whatever size of the window is there. We'll sum and square. So this is the formula for calculating short time energy. That is signal first multiplied with a short time window and then window. Normally rectangular window or Hamming window we are using. So this is there. In this way, first we calculate short time energy. Then zero crossing, you know, when you periodic signal, it will cross zero because first part positive, negative, like sinusoid wave, it has to be some positive part, some negative part. So the point where zero is crossing, that is deciding how we will calculate the frequency. That is, for example, if signal is having 50 Hz, that means in 1 second it is changing 50 times. That is positive to negative, negative to positive, that is zero crossing. Similarly, we can calculate zero crossing rate, counting number of zero crossing. This will help to us to calculate fundamental frequency. Zero crossing rate is a simple measure of the frequency content of the signal. Sinusoidal at frequency f0 with sampling rate fs has fs by f0 samples per cycle with 2 zero crossing per cycle. In one cycle, one positive, one the 2 zero crossing, giving an average zero crossing rate. So this one can use as a formula 2f0 by fs as a number of zero crossing rate. Or we can calculate zero crossing rate z, then we can calculate f0, that is z equal to fs by 2. So this will help us to calculate pitch frequency. In this way, you can calculate fundamental frequency f0 called pitch frequency. This is the typical spectrum. You see the focus on the spectrum. For unvoiced part, high magnitude region will be in this envelope, high magnitude region will be in high frequency. In voiced part, in lower frequency. That means lower zero crossing rate. One can say unvoiced part, the dominant energy is about 2.5 kilohertz. And in voiced part, the dominant energy comes about 700. And that's why zero crossing is lower in case of voice section and more in case of one voice section. For example, for unvoiced speech, energy is mainly below 3 kilohertz. And for unvoiced speech, energy is above 3 kilohertz. That means average zero crossing rate for unvoiced is 49 per 10 millisecond. If you are taking frame of 10 millisecond and zero crossing rate is coming 49 and above, you can easily say that section is unvoiced section and no need to give any attention to that from a speech signal point of view. If mean zero crossing rate, average zero crossing rate is below 40 for 10 millisecond frame, and that is a voice part, and you have to focus on that because information is there. Information of the speech signal is contained. From the speech processing point of view, will not give attention to unvoiced part. That means if zero crossing is more than 49 like that for 10 millisecond frame, or if it is less than 14, we have to give that attention because that is actually voice part. So that is in the same in the similar pattern, we can calculate autocorrelation, but not autocorrelation for entire signal. It is autocorrelation for short time. That means we'll take signal XM, multiply by window. And then same thing is shifted. This will be the formula for short time autocorrelation. It is standard formula. That is signal, shifted signal version. This gives autocorrelation of a signal. We need short time, that will multiply by window. Signal, shifted version, that will give autocorrelation of signal, but signal multiplied with window. Then signal shifted, window shifted. This will give autocorrelation that we call as a short time autocorrelation. And short time autocorrelation, short time energy calculation is used in speech processing. Reason we are doing using short time frames, frame by frame calculation we are doing. Select a segment of speech, and that is by windowing, and compute deterministic autocorrelation of the window. Like autocorrelation, this short time autocorrelation is also a even function, even symmetric. Okay. We can define like filter in the form of filter, that this Hn Wn plus Wn shifted form. We can give a name as a filter like H. We can represent like this autocorrelation. This is a standard formula. if people from DSP background is very much familiar. Spectrogram, and that is short time Fourier analysis. We know Fourier analysis, but here what we'll do? Short time Fourier analysis. That is, will not use the entire signal for short duration, and that will call it short time Fourier analysis. So in that case, the time, what frequency content is there, and what magnitude. That means representation of magnitude, time, as well as frequency. That's why we are named spectrogram. This will call it spectrogram. We are using wide band spectrogram. We are using narrow band spectrogram. If we are analyzing a frame of 15 milliseconds, we'll call it a wide band spectrogram. If this window size is 50 milliseconds or more, that means if window size is in time domain smaller, that is wider in frequency, and that's why the wide band spectrum. That's with the name. And if narrow band, if window is of larger size in time domain, it is frequency domain of smaller size. That's why narrow. So what this observation, we'll see the diagram, we'll see the observation. Okay, what observation we are getting from spectrum? Similar observation. See, this is our speech waveform. If we'll do a spectrum, that means we'll take a frame, we'll do Fourier analysis, and we'll plot short-time spectrogram, that is wide band spectrogram, narrow band. What observation is there? In wide band spectrogram, we can see this vertical strips, and this darker region shows high magnitude. You can see, you can easily identify the darker region, the first band. Similarly, in horizontal strips is observed narrow. From that, we can analyze the formant frequency. This part is F1, F2, F3. On spectrogram, you can see. And that will come only out after the experience, when how you are analyzing the spectrum. That is taken from, again, Rajesh and Sheffer group. Actually, this type of diagram will observe when you will implement on MATLAB in color diagram. This is the spectrogram. Like, should we change it? This is spectrogram is for this. Okay. So this strip, you can see, easily strips are same. Okay, and you can identify this is a horizontal strip, this vertical strip. This is a wide band spectrogram. This is this narrow band spectrogram. But this will come out from after the experience. If you are working in this area and finding so many spectrogram and analyzing things, then only you observe. It is again from Rajesh and Sheffer. So first part we have seen, that is speech production. Similarly, speech, hearing, and perception. When we talk speech, hearing, and perception, again biology involved, and that is also need to be modeled. How frequency distribution is there through the basilar membrane, so it is there. Pinna is collecting, and sound is coming through the auditory canal, and here the eardrum is there. Here, melcus, incus, okay, steps. So this part is called outer part of, this is middle part of the inner part of ear. And finally, they are coming on this. This is a semicircular canal, round window, this oval window. They are coming for project cochlea. Cochlea has different point. It is acting as, you can say, a different point. This amplifier, signal of different point frequency will be amplified at different points, or you can say frequency separator. Then impulse will be generated to excite this auditory nerve, and you will give the information to your brain. This the role of cochlea. That is, this outer part is the space, this is the apex, and at different point when this sound is like is coming after processing, it will like this. At different point, different frequency sound will be going to be separated out like that. That means it is frequency separator. This can be, that means from DSP point of view, this can be implemented as a filter bank. This high frequency part, this is not a high frequency. Actually, this is a round window, oval window. The complete cochlea is of the shape, a snail shape like that. This is called apex, where lower frequency are going to be amplified, and as this outer part, the higher frequency, different type of mediums, that is fluids are there, and that's why different frequency separation like that. The middle and inner ear mainly perform the mechanical filtering, the outer part, middle part, inner part. So first is mechanical filtering. All those, the mainly sound is now separated from this cochlea. Okay. So the cochlea is a snail cell structure filled up with watery fluid in a cross section of oval and round window, and is a frequency place separator. At different place, different frequency will be amplified according to frequency from low to high. That is there. And the dynamic compression of the intensity of this thing provides the basilar membrane of the cochlea according to frequency. So there will be gain adjustment, you can say like that. This part, intensity of the sound is going to be adjusted here. And for the sensation of the signal, a neural spike at that base of the nerve is only generated when the stereocella of the inner cell are bent one way. So that is acting as a like half-wave rectifier. You can say there is a filter bank. How this human auditory system, main important points: filter, bank for different frequency, cochlear representation. And then one side representation is giving response to the auditory nerve, that is like half-wave rectifier. Then there is a gain adjustment. So these three things are there. Okay. And then there is cognitive mapping in the brain for perception. So this is human auditory model. Then first this, when we are talking about now processing, that is the human auditory part. Then processing, then first we are taking the signal in any form, then passing through a pre-emphasis filter for pre-emphasizing the signal. When we are going for processing of a speech signal, we'll first pass through pre-emphasis filter to boost up the high frequency, and it is easy to now separate out. Okay, so this pre-emphasis filter is a low pass filter. Then we'll find features. A wide range of possibility exists for parametrically representing the speech signal. These include short time energy, zero crossing rate, zero crossing short time autocorrelation. So these things we can calculate. These are things we call here as a features. These are time domain features. So we understood the speech production, we understood the speech perception. Speech production is again like excitation, pulse model, glottis model, lip radiation filter, like a model. Similarly, receiving and human auditory system, like a model, filters, bank of filters, like filter bank, gain adjustment, okay, half-wave rectifier. Then we'll focus on features. Features may be time domain, like short time energy, short time zero crossing rate, short time autocorrelation. So these things we have to calculate from digital signal processing point of view. The basic, most widely used parametric representation like LPC coding, all these are itself is a separate point of or topic of webinar. But after understanding the speech signal in production part, speech signal in perception part, finding the different features, how to find the different feature. This is all these are we have seen in digital signal processing tools. Perceptual linear predictive modeling, PLP modeling we are calling. Relating the spectra, all these are the tools of DSP. Mel frequency captions, we are talking about frequency. When frequency converted onto Mel scale, on log scale, that is the Mel frequency and capsule coefficients. These are as a features. As decided, speech in two parts, voiced, unvoiced. We'll leave unvoiced part. For voiced part, from production point of view, from transmission point of view, and perception point of view. Voice part important. For voice part, on frame by frame, we'll calculate the time domain features, we'll calculate these types of features. And on that, features comparison, features adjustment, and all those are the processing. This is called speech signal processing. Finding these features, playing with these features, comparison, and working with these features will be now working of speech signal processing. So this is a typical block diagram for calculating, for example, the most popular feature, and that is the Mel frequency capsule coefficient. Like a continuous speech that will pre-processing, passing through pre-emphasis filter, and from frame blocking, then finding Fourier transform, its magnitude, squaring, then wrapping on Mel scale, then taking its logarithm, DCT, like that, discrete cosine transform, the coefficient we can get them. So this is you can this is a again you can see the how to calculate MFCC. All these ready-made even MATLAB codes are available online, and a lot of algorithms are available. So this is the most important feature. MFCC one can calculate for speech signal and for different frames. And the applications part, like speech compression, coding, we have to focus on, as discussed, we have to focus on the bias part for coding. Similarly, for quality, or if quality is degraded, we can enhance recognition of speech and speaker. Every point itself is a topic of webinar. But in short, we'll just go through that in brief, so that we'll have just idea of that. In speech coding, a simple PCM coding we can do, that will give 64 kbps bitrate. Simple calculation, like a speech signal, you have sampled, for example, 8 kilohertz. Each sample is by 16 bits or 8 bit. If you are evaluating by 8 bits, 8 into 8, that is 64 kbps. If you are evaluating 16 bits resolution, then it is 128 kbps. Pretty simple mathematics. And all you are knowing with that. Adaptive PCM, it can give bitrate below that and up to 32. And LPC even can give 20 kilo. Vector quantization model, which can reduce the bitrate up to 8 kilo. And even new research is motivating up to 4 kilo. So a lot of algorithms are there to reduce the bitrate, speech coding, so that information is not lost and speech transmission at low bit is possible. But here issues are quality, because when you will reduce the bitrate, quality is going to be affected. Also, there may be positive time delay, complexity will be more. So these are the issues of speech coding. So this is a brief idea about speech coding. And when you talk for quality, quality is again why you are measuring quality. Okay. For network system design development, it is important to know the quality for customer satisfaction, customer service, and for continuous monitoring of a network, selection of speech codecs, speech speaker recognition. The speech quality is to be what quality is speech signal enhancement if quality is below the threshold. For telephone network, mobile communication, voice, everywhere there is a requirement of measurement of speech quality. That is whether it is up to the level or it is more degraded. Then more degraded, then need to be enhancement, speech enhancement. So that is there. Different speech quality estimation techniques. The main is either listener will listen and rate it, and that is the ideal method. But practical method is objective quality. There should be some mathematical algorithm which can say about the speech quality. And this model, one is called intrusive model, other is called non-intrusive model. So we can measure a speech quality by intrusive when we'll use a reference, original signal, and what were their features, and what is the features of received or degraded signal. We compare that. And non-intrusive does not compare. So that is the difference. Yes, signal is there, system under test, received signal. If we'll take the feature of input signal and received signal, if we will compare, then it's called intrusive technique. And if we'll only use the received signal and if give that is called non-intrusive, either by listener or by different IQT standards are there. For intrusive, it is recommendation P863 in existence, and from a listener, it is ITUT recommendation P800 is there. So there is some standardized technique is there. And for non-intrusive, it is ITUT recommendation P563. MOS is called mean opinion score. It is listening quality objective model, and a listening quality objective model mean opinion score. And this is subjective model. That's why mean opinion score LQS, listening quality subject. Yes, subjects will listen, listener will listen, and then average, that we call as a mean opinion score. So this is about speech quality. That is about speech coding, speech quality. If quality is not up to the level, then there is speech enhancement. Then another important area, that is speech recognition. All you are familiar that speech signal is there. You have to recognize what it was said. Machine which had to understand. So like here, what we'll do is take the speech signal, we'll calculate features, we discuss time domain feature, frequency, or different a number of features we have discussed, most important, and like MFCC. So those will there. So phoneme recognition, that will be compared from word pronunciation, and that is we can use here semantic knowledge, dialogue knowledge, and then sentence recognition. We can make the decision. So this is a brief block diagram of a speech recognition system. Similarly, speaker recognition. So these are other major areas, and each area, in fact, is a point of subject of like a speech signal. Speech recognition is a separate area. It's language recognition. Which language? That's a speaker, who is speaking, the person who is speaking. So this is the speaker recognition. Again, this recognition is speech, separate part. Language recognition is separate part. Speaker, who is speaking, like that. That is it. Other important part, identification. Whose voice is this? To identify a number of speakers are there. So it's whose voice? This is the speech identification problem. Again, a speech verification problem. Like someone is claiming that I'm the Rajesh. So is it verified? That is the speech verification authentication problem. And similarly, segmentation, clustering, all these are the speech. Where the speech in there, all these are the speech processing applications area. And each application area itself is a topic of webinar. So in briefly, I tried to explain what is speech production, what is speech speech production model is, how it will model for digital signal processing people in form of a digital filter, and then how it is speech is coded, how it is transmitted, and then how it is received. Then receiver will receive human auditory model, how it will modelize filter, bank, and from a DSP engineer point of view. So all once these are modeled, just applying DSP tools in time domain, in frequency domain, we can calculate different features, we can compare features, we can play with features, we can analyze the features for different type of applications, whether it is speech recognition, whether it is speech quality, whether quality enhancement, whether speech or speaker identification, verification problem. Everywhere we have to play with the speech features. In all these applications, speech features of voice signal part. Unvoiced part will leave the side. We'll take a speech signal, we'll identify the voice part, we'll calculate the different types of features, and depending on applications, we can apply the different types of features. Whether it is time domain, whether it is frequency domain, whether it is combination of features, like that. So that is there. Is there any question?
Yeah, thank you so much for the presentation, sir. If you have any questions, you can just put it into the comment box, and we'll try to answer them as soon as possible, because this will take some delay. Like in YouTube Live, it will be a delay of 10 to 15 seconds. So if you have any question, you can put it in the comment box, or otherwise we'll try to provide the email ID of Dr. Rakesh sir, Rajesh sir, in the description box, so that if you have any further questions, or if you are watching it after a few time, you can just directly ask to them via email. So I would like to thank all the participants who were live here. Also, I would like to mention this this webinar will be available on our Research Circle YouTube channel. So if you are not available on this time to watch it live, you can just go to the Research Circle YouTube channel and you can watch it again. So I will be trying to share the link in the group of this particular webinar, so that you can directly just check out the session link. So thank you so much all, and thank you so much Dr. Rajesh Kumar Dubey sir for taking out the time. And
thank you very much.
We hope another session from your side in the near future with the another interesting topic. So thank you so much, and I want to take the leave with your permission.
Thank you very much.
Thank you so much, sir.